All right, well, thank you all for joining. Today we have Nicolò Botteghi coming from the University of Twente in the Netherlands. And he's been here all week and we've been having lots of great discussions about reinforcement learning control. And today he'll be talking to us about data efficient, robust, and interpretable deep reinforcement learning for robotics and dynamical systems. So we'll go ahead and get started. Thank you, Nico.
Hey, Nick, thanks a lot for the introduction. It was super great to stay here this week, and I'm super excited to show some of my research I've done during my PhD and postdoc in Twente. So first, I'll give you a little bit about introduction about myself. I've done bachelor and master in automation engineering in Bologna, my hometown in Italy. Then I moved to the Netherlands for like a postdoc in a PhD in robotics and mechatronics, and followed by a postdoc in applied math. In my research, I try to combine a bit of theory, method, and applications, because I believe the synergy of these three things is what really can impact the society and science a lot. So I try to develop expertise across machine learning, control, robotics and dynamical systems, and then been trying to collaborate with many researchers from different fields. We like the different perspective that the different field can bring into the projects. I've been, during my years in Twente, I've been teaching assistant to lecture in control engineering and deep learning courses, and I've supervised a bit more than 35 master and bachelor students in their final thesis graduation assignment throughout the years. My driving force, a bit of curiosity and passion for learning and research and studying. And well, in my free time, I train for triathlons. I like a lot cycling and hiking. So some research project I've worked on throughout my year. So this is from my master thesis. We looked at design and control of the cheetah robot with compliant spine. So the idea is that, well, differently than what you see the robots nowadays, like leg robot with like a very rigid torso and legs, we try to take the biomimetic approach and see if we can design something that was energy efficient by relying on like a compliant spine, also serious elastic actuation. So really try to take the nice features of nature from the cheetah, because we try to look at energy efficient locomotion. So we look at the fastest runner on Earth, although, well, the outcome was more like of a rabbit. But the idea was relying on biomimetic. A lot of things become simple. For example, like the controller is going to be just about sending some square waves to the actuator, some pulses to excite the dynamics. And we can make, by changing the phase, like phase shift between the, let's say, right side of the body and the left side of the body, we can do these cornering maneuvers and do some form of control. So this project for me was really triggering my passion for robotics and control even more. And after that, I decided, okay, let's keep working on this for like during my 4-year PhD project. I finished after 4 years of blood, sweat, and tears at the end of 2021 with thesis entitled Robotics, Deep Reinforcement Learning We Lose Prior Knowledge, where the idea was really, okay, we know that this reinforcement learning is a powerful tool, but on the other side, it takes a lot of samples. It's not robust, it's not interpretable enough for like a real world application, in this case, navigation. And I try to look at different perspectives of how can we encode prior knowledge into the learning process to improve performance, namely in terms of, for example, sample efficiency and so on. I will show you later on more details about this project. And well, after that, I wanted to develop a bit more my mathematical knowledge, more theoretical knowledge, and I moved to the Department of Applied Math in Twente, where I try to focus on spending time in learning about dynamical system, partial differential equations, a bit of geometric deep learning, and asserting quantification. So try to see what are we missing to, for example, do reinforcement learning of partial differential equations. So let's start with after this brief introduction, let's start with the talk. Well, in our everyday life, we see many examples of dynamical systems, so system evolving over time. You can see like you can figure bird flying patterns appearing on certain animals, the weather, robots, and understanding, predicting, and controlling these systems is crucial aspect for science and engineering. And while for simple systems, we can rely on physical laws to describe their evolution and control them, for many complex systems, we don't know the physical laws, or even when we know them, the computational model derived is simply too expensive to use, and we have to trade the accuracy and the computational complexity. So, however, for these many systems, we can gather abundance of data that we would like to use in a smart way to learn and do control. However, despite the fact that we may have a lot of data are high dimensional, are noisy, so it's very, very challenging task.
Would you mind hitting that little X
Oh, yeah.
there? You,
Do I get
there we go. Perfect, thank you.
Yeah, you're welcome. So, well, in my research, I'm very interested in, I work mostly on trying to solve control problem using reinforcement learning from high dimensional data. So now I will give you like a very brief introduction on reinforcement learning. You probably know about it, but I just give you just quick intro. So many real world control problems cannot be solved with a single good decision, but require like a sequence, maybe even long, of good decision. Think about making coffee, like already starting with the grinding size. Well, if we don't know it, it's very challenging. And the trick is that, well, this decision that I make on the dimension of the beans or the grinding, the size of the grinding, affect the short term, but also long term. And only in the long term, so when I drink my coffee and it's maybe trash, then I see, hey, I did something wrong, and I have to be able to go back to that decision. And that's really very, very challenging to take this into account, because clearly, like the more I look into the future, the more you have uncertainties. And when you want to go back to the decision that brought you to this reward, let's say like the quality of the coffee, this is very challenging. How can we solve this problem? Well, reinforcement learning is a way to study these problems. In a bit more formal way, we can identify in reinforcement learning two main entities. So the agent, which is the decision-making entity, the controller. So it's a very general framework. So here you can really put whatever you like, the controller of your robot, whatever you can think of as agent. The environment, so it's the world in which the agent lives. And it's basically my system that I want to control, but not limited to that. In reinforcement learning, we make no assumption on the kind of information about the environment. So it can be unknown, linear, stochastic, complex. We don't know. Everything can be included there. We have the goal of the agent, which is learning to select the actions to perform the task optimally. And the optimality in reinforcement learning is defined by the maximization of the total cumulative reward, which is controlled with negative of the cost. So how does this learning process work? So we have like this agent environment interaction that occurs through the action. So for each moment in time, the agent can observe something about the world. I call them observation. Could be, in certain cases, like the full state of the environment. So the full amount of information we can get from the environment for control, but sometimes we have partial measurements. So we can't observe the whole world. Like if I have a robot navigating with a camera, I can only see in front of me, but I don't see maybe the back of me. And I don't know exactly maybe my position in a room, because from a single image it's hard to capture. So from this information, the agent selects an action, applies it to the environment, so applies the control, and receives like a reward. So telling how well this action was in terms of the reward function I'm trying to optimize. This interaction is very, you can imagine that when I have no assumption on the word, the agent doesn't know which are the optimal actions, and it has to kind of first explore, so try actions that are new, and see if it can collect higher rewards from there, or just follow the optimal policy, so what the agent thinks is the optimal policy, and then maybe, so you have this, what is called this exploration-exploitation trade-off, here that is also one of the key feature in RL. So deep reinforcement learning. So when we want to scale to high dimensional systems, we can use deep neural network for approximating our control strategies and value functions, where the value function tells us what is the total cumulative reward I can collect if I start from a given state and I follow my current policy for a certain horizon. So we can do that. We can scale to a high-dimensional system, continuous state space, continuous action spaces, and there's been quite a lot of hype and success in the past years in terms of robotics, games, and so on. However, for example, you want to look at flow control or control like a robot in a fluid and move towards even more complex real-world problem, we face quite, like, I highlight 3 main challenges. Of course, there are more, but I think these are, in my perspective, the most relevant ones. So we have a problem of sample efficiency. So learning from high-dimensional data, I will show you in a couple of slides why it's sample inefficient, but meaning we need a lot of data to learn something meaningful. We struggle with normally generalization. So if the system changes a bit, we have a system that has some parameters that we don't know, they change a bit, and the policy most likely is not going to be optimal anymore. And we have like an issue of interpretability, because we get like, even if we get like an optimal policy, somehow it's still like a big black box neural network that it's hard to interpret. We don't know what happens if we feed some new data. It can be like a totally different prediction, which can be in certain application, like safety critical application, a real issue. So in my research, I tried to take upon this challenge. So I will show you a couple of 3 projects I worked on going towards that direction. So the first problem is, okay, why deep reinforcement learning is so inefficient when we deal with high dimensional data? Well, if you think about it, what we do in reinforcement learning is that we rely only on the reward signal to learn the policy and the value function. So we have a signal that may be even sparse, so we may not get the reward at each time step in many situations. For example, if I want to make a coffee, I get the reward only after I drink the coffee. So many steps ahead in the future. So using only the reward signal means that these deep neural networks that we have have like a very, in many cases, a very uninformative and weak gradient to optimize their parameter. So if we take this example, and this like a bit of the work I've done, we have a robot navigating. You see like these points here are the states, the possible states. The robot is in a room, and the black are the walls. The color gray represent the reward. So ideally, we would like to reach the target here. And we don't observe the state, but we rely on sensor measurements. So we have like a camera image here, it's a bit cut by this, but I will show you later on, and some proximity sensor information. So the idea is that, well, once we have this high dimensional input, it's a good idea to learn a representation of this data, and then try to, using unsupervised learning techniques, I will show you one in a sec, and then learn a policy given like this compact representation. So the idea is that we don't want to only use a reward signal to learn these features, but we want to use other techniques. And if we consider like a robotics task, and we have prior knowledge, we should exploit them as much as possible. So here is a bit what I was describing before. We have the classic reinforcement learning loop. We have like an agent navigating in some environment. We have camera images and laser range scanner information. And from this information, we want to learn like a low dimensional representation. So Z of T has a way smaller dimensionality than the input. So here we're dealing with images, quite a lot of pixels. And here we are dealing with something of the order of 5 dimensions. So very small state space. And we have like a reinforcement learning network that you can learn from here. So I identify here with this phi encoder, this neural network that takes input observation and maps it to a state. So what you could do, for example, you can view this as the encoder of an autoencoder, have a decoder, learn a reconstruction loss, fine. But I mean, this does not add any, we're not using any prior information about the actual state space we want to have. So the idea is that in robotics, we know that, for example, the state space is going to be smooth, right? Like from one measurement to the next one, the robot won't teleport. At least in 2020, when I wrote this paper, robots would not teleport across space. Maybe in 1,000 years, they would say, hey, this guy was really stupid because it made no sense. But for now, this is a prior that we can exploit, and actually we want to exploit, right? Because, and this is something with the autoencoder won't capture, because let's say autoencoder is focused on really visual features. If my robot rotates just a bit and it faces like a wall of a totally different color, it's going to place this embedding far away in the latent space. So there's not going to be any temporal coherence in this representation. And well, one of the prior we use, we call it temporal coherence loss. And we use it for encoding precisely that. So we know that state changes are slow, everything is smooth, and we want that, well, we want to kind of also reconstruct the Markov decision process underneath. So we want to also that this state here, this latent state, captures all the information in a Markovian settings fashion. And the idea is pretty simple. We have a couple of consecutive observation, an action, and we try to minimize the distance in the latent space of consecutive states. It is a bit like the picture. So we know this property in the real state that we can't observe, but we observe measurements, but we know that in the latent space, we would like that the latent space behaves like in the true state space that in which the robot lives. A second example is what we call proportionality loss. So again, we have like a loss function that takes consecutive pairs of states and tries to regularize these transitions in proportion to the similarity of the action. So, intuitively, if I am in two states at two different time steps, which looks different, but we apply the same action. I mean, if my robot is in this location of the room and it moves 1 meter to the left, it's going to be the same as if it's at the bottom of the room and it moves 1 meter to the left. So that's a bit the idea. Try to use the similarity of the action to add an additional regularization to the state space we're learning. Because again, we're using no decoder, so we just have an encoder network and we use these kernels to shape the representation. So clearly, we need like also, I'm not showing it here, but we need like an additional contrastive loss to prevent the collapsing of the embeddings, because here all these losses in a sense push pairs of state to the zero state. I mean, there is a trivial minima of this, but with contrastive loss, we can just prevent that. So, yes. Yes.
Yeah, and so for maybe for example, harmonic action, so that's how we would be very small, right? Something, and in that case, so how does that actually be? Like,
Oh yeah, basically it scales.
You repeat the question, please.
Oh yes. So the question is, we have also this action term here. How does this term here affects the representation? So yeah, thanks a lot for the question. Indeed, I didn't point it out. So the idea is that, well, we just want to keep these states close to each other with the magnitude proportional to the action taken. So if I apply a big action, for example, I'm swinging the pendulum, if I add like a lot of torque, I expect that the latent states are going to be a bit further apart. Well, conversely, if I apply a little action, I want that this, so I think this exponential of minus alpha action does precisely that. So it takes into account the action to change a bit how much we should push these two consecutive states close together. Yeah, thanks. Yeah, so some results. We have additional results in paper, but I didn't include them. But I mean, it's just like the reverse plot. We show that it works well, but that's maybe less interesting. And so here we see some example. We have, again, these are the states, the true states of the robot, so position and orientation with respect to the reward. So we have this room, we have this little robot here, and we want to navigate to this target. We collect this bunch of data with the, well, basically for each point here, we have like an image and an RGB image. And we use this kernel loss function to learn this representation, and we project it. Now, this representation is going to be 5-dimensional. We use a PCA to project it to a 2-dimensional space such that we can visualize it. And you can see that we can do a fairly good job with the first two principal components to capture the actual smoothness and structure of the state space. So this for us was very inspiring, very exciting, because we were able from images to reconstruct something that looks very much like the true state space of the robot without doing any supervised learning tasks. So we don't observe the states directly. And we also compare with other methods, but I think one was quite interesting was what happens when you use an autoencoder. First of all, with the autoencoder, you cannot really reduce to dimension 5, because otherwise you can't reconstruct at all the measurements. So already this latent space with the autoencoder is going to be like 4 times bigger. And when we look at the first two principal components, we cannot really capture, there is not like a very good correlation with the actual state variables, meaning that the control task is going to be more difficult. And well, eventually, for us, we wanted to solve real-world problems. And the idea was, let's see if we can train in some simulated environments, and we just deploy the policy in the real world without any need for training on the real data. So we did some little tests where we add also distractors, so visual feature that the robot hasn't seen before during training. And it seems still quite robust in its behavior. And that for us was very nice results, because we didn't need to do any training with real world data, which can be very expensive, costly, not safe. We also here try to, turn off the light and see what happens, but the robot was still kind of in a searching behavior that hasn't been seen over training at all. And then once the lights are off, you can really detect again the features. So we tried also like in a bit larger environment in a SEC, yes. So again, simulation platform that was not very photorealistic, but we are still able to do this transfer learning thing. So we were very happy about these results. So towards open challenges. So we saw here in this project that, well, regularization using prior is a powerful tool for reducing the need for data, being able to learn compact representation that are robust and can bridge the gap from simulation to the real world. But well, we know also from recent work on geometric deep learning that if we have, for example, in a physical system conservation laws, we can derive some symmetries and we can encode them into the architecture by construction. So how to do that in control settings, which for me would be like something I would like to investigate a bit more. There is this theory from the 2000 on MDP homomorphism, where MDP stands for markov decision process. So the idea is when we want to do dimensionality reduction of like a very complex Markov process, so you can think here, the example of before, here we have high dimensional measurements of the system. We would like to learn a representation such that we can learn a policy in this reduced space with less data in an easier way. So the idea is that, well, we can cast this problem into like a learning problem. And I think the nice thing of this framework is that allows us in its exact version, which is not what we're going to solve, but I mean, we're going to solve an approximation of this problem, allows us to, when we have like an optimal policy for this latent MDP, we can bring it back, we can lift it to the original Markov process while maintaining its optimality, because I think it's very important that when we do dimensionality reduction, we learn a reduced policy. This reduced policy is also optimal for the original problem we want to solve. And I think this is a nice way of doing that. And in a sense, this mapping H and F of S that you learn to reduce the space, are you going to encode some symmetries of your problem? So that's where I call symmetry discovery. we can do even better. So if we know some symmetries, we can look at this group structure MDP homomorphism. So we can really encode these symmetries in this mapping. So we can just look at the groups and apply them with this simple rule. So here the idea is that, again, we have the car pole, we know we have some symmetry. So moving from a certain state to the left is like gonna lead to the same as if you do the same for the moving to the right. And we can encode these. So I think this is something that I've been investigating a little bit, but I think it's something that would be super interesting to try out for like for example, like a flow control or PD control problem, because this framework has been tested for very simple settings like the car pole, but I think there is a lot of potential for looking at these dimensionality reduction schemes in the context of flow control. Nick pointed me a couple of weeks ago to this paper on cluster control, which I think definitely has some connection with what we're doing here. And I think another exciting work done here from Nick and Sam Otto, looking at also continuous symmetries, because these frameworks have been introduced for very simple problem with discrete symmetries. But I think like looking at continuous symmetries would be very, very exciting as well. So second project, still in the ballpark of control. Well, we know this work that I did with my colleague Urban, former postdoc here. So we know that many systems in engineering and science can be modeled with partial differential equations. And although like the optimal control of these systems poses a very tough computational challenge due to the numerical, due to the fact that we need to numerically solve the PDEs many, many times. And this is even more severe when we have, for example, parametric PDEs. So for each new instances of the parameter, we have to resolve the PDE and find the new controls. So in this work, we really precisely look at this problem of controlled parametric PDEs. So looking at really the generalization aspect. So can we learn a control that can generalize across different PDE parameters? And can we do it in a way that is robust with respect to noise on the measurements, but also interpretable? So again, just a reshaped version of the RL control scheme that you've seen already a couple of times. We have now in the environment RPDs. We look at these 1D PDEs like the Kuramoto-Sivashinsky and the convection diffusion reaction. I will show you some results later on. These PDEs have some parameters that we can observe that are the varying parameters. And we have some measurements across the spatial domain. Again, I think here we don't assume that we have full access to the state of the PDE, but just to a part of it. The idea is, I think we were obviously heavily inspired by the CNDRL work on approximating the policies a posteriori with some sparse dictionary models. And here we started with the assumption that, well, the control policies normally are pretty, like an optimal control policy normally is pretty a smooth function. Maybe it has like a peak, but then it kind of, it's not like a super complex function. It's hard to find, but it's not necessarily super complex. And when we parameterize this policy with neural networks, well, we are obviously over parameterizing them, meaning we need a lot of data to learn these parameters. So we look really at what if instead of using a neural network for representing the policy, we directly use a sparse dictionary model, sparsify with like a differentiable at 0, that we can really plug in any reinforcement learning algorithm instead of the classic neural network. And we can use it to just directly plug and play and learn a policy that at the end of the day is going to be also something interpretable. A little bit of a zoom in of these. So we have the PDE parameters, we have the state, we concatenate them, and these are agent state. We use a polynomial feature library of order 3, but in principle, like any library, depending on the task and the prior knowledge you have about the optimal solution, you can use different things. And to cast it in a more kind of reinforcement learning friendly settings, you can view this feature as input to one single layer neural network that is sparsified using like an L0 mask. So the challenge was that del zero, it's normally not differentiable. That's why, for example, like you can rely on a L1 or a truncated L1. But we really wanted to kind of see if we can cast these problems really in terms of a zero settings. How to do it? So again, learning these binary masks for the weight here, it's very yeah, you can't do it in a gradient-based fashion. And reinforcement learning algorithms, they work with gradients. So we needed something we can really cast there. So the idea, and well, came from this paper. And I think this summer with Urban, we wrote like a bit of an extensive tutorial on how can you derive this zero mask and how can you apply this model that we developed, not only in the context of approximating policies, but also transition models, reward models, and other things that are helpful in RL. But the whole idea is that we can have this gating mechanism depending on like a distribution that is parameterized, where the parameters are learned. And the idea is that like our regularization basically becomes calculating the probability of the gate being active that is described by this. So I'm not going too much in the details, but we try to make it nice and educational, such that maybe other people can also enjoy this. But yeah, that's the way we use, that's the method we use in combination with the sparse dictionary model to learn the policies. So I'll show you some results on this Kuramoto-Sivashinsky PD. Is this PD here? We had this forcing cosine term that is a function of this mu parameter. We have some Gaussian actuators spread uniformly across the domain. So we only have 8 actuators. So we don't control, we're not fully actuated in a sense. And the idea is really, well, we train our agents with the limited instances of the mu parameter, and we try to generalize and evaluate this agent in a larger range. So really to test the generalization capabilities of this agent. So we compare with the, let's say, the L0 sparse polynomial free is what we developed. We try to replace the L0 with the L1 to see if this masking with the L0 actually makes an impact. We use the TD-free, this is a state-of-the-art algorithm. And we also look at what if we don't pass the PD parameter in the state, if it makes sense to use this information. So here you can see some results in terms of interpolation. So there's a mu value that hasn't been seen during training, but is within the range of variation of parameters. And you can see that here in terms, well, the task, of course, is defined here. We want to track the state of the PD to a reference value that is 0 in this case, and we want to do it with the minimal control effort. Classic cost function that we can use in control problem. And you can see that in terms of the cost here, with L0 mask, we can do very well. Even with L1, we can do very well, or at least way better than if we use a neural network for representing our policy. And also here, it's very interesting because if we don't include the mu parameter, yeah, apparently, well, this mu parameter is very important for deriving a good policy. So extrapolation, this is even more interesting. So this is a value outside the training range, and we can see that we can still do a very good job here. Although, I mean, you can see that the PD is quite, the dynamics is, it changes a bit. There are examples where it changes more, but I think these results are quite consistent. And you can see here that in extrapolation, for example, these TD-free, these neural network-based models, they don't work well at all. And they also rely on way more control effort in general, which is also bad because we want to do also, I mean, I want to develop a nice, good policy that can control my system, but I want to do it also with the least control effort. And yeah, very nice addition is that at the end of the day, we get policies of this type. So despite the fact that, let's say we have 8 measurements, so our state combo 8 measuring 1 parameter. If we go for a polynomial of order 3, we have quite a lot of feature, around 1700. But still, after training, we can get policies with 6 terms, 7 terms, which are very, very compact and interpretable. You can see also, you can do some analysis. We haven't done yet like any stability study robustness analysis yet, but I think you can see at least that, for example, the action 4, which is going to be located somewhere here, it's dependent on the measurements at location 4, so on the local measurements, on aviation measurements, so the M3, but also on non-local information, for example, this M7. And this policy also depends non-linearly on the PDE parameter. So you can see like a mu square, and like a mu cube appearing. And the same for this action 8. So you also see that the mu square, the mu cube, they also appear here. And you have this interplay between local measurements and no local measurements. So indicating that for these kind of tasks, if the reinforcement learning agent has a more global view on the state and can really, which is a bit in contrast with the works on current multi-agent RL, where each agent is local, independent on the rest. But here it shows that I think if you have some form of coordination in between the agent, you can really improve a lot of the results. So some open challenges. We worked this summer with Andrea Manzoni from Milano, Urban, and Florian on to extend this framework to high-dimensional systems, because obviously we are a bit limited to the size of the state space with the dictionary learning. And I think we went also towards a bit more model-based reinforcement learning. So you can view it in a way as a little step towards like a SIMDRL framework from high-dimensional input. So the idea is that we want to learn a transition dynamics in the latent space, and we use some autoencoders to reduce the dimensionality of state and actions. And then we do in model-based fashion just a few interaction with the real world, a lot of interaction with the simulated world. And we tested in a couple of 3Ds, 1D Burgers equation and this 2D cavity flow. And it seems to be working quite well. And very important things, we can reduce by a factor of 10 the number of interaction with the real world, which was really exciting and motivating for us in continuing developing along these lines. Second aspect, we've been looking a bit with Urban and Adrian, a PhD student, Urban's PhD student, this problem co-design. So how can we on one side learn a policy, optimal policy together with some design parameters? I mean, the design parameters can be, if you have an airfoil, the shape of the airfoil, but also can be like the PDE parameter as well. And we were discussing, okay, if we have a very large, obviously parameter space, design space is very complex. And well, we've been chatting a bit in the past week with Nick as well on maybe relying on active subspaces to really look at what are the important design parameters for optimizing policy. And yeah, eventually a few years back, a couple of years back with my colleague in Twente, we tried to go in the wind tunnel. We had this little setup controlling this flap, and I think it's a bit covered here, but you have like a little pressure sensor. And we want to try to do flow control. Although I think so far I've shown you successful results, but this one was a total, not total failure, but like, let's say we learned a lot from it, but not maybe the thing we wanted to learn necessarily. But yeah, one thing was really for me, striking that even in this simple case, you want to just control the angle of the flap to maximize lift, minimize drag. Last thing, already like doing it in a wind tunnel was super difficult. You have to account for so many things that we never really push it through like a full publication. But I think it's something that I really liked, enjoyed, and I think, yeah, in the future I would love to go back again and see what I can do in this direction. So for the final project, so we looked at with my colleagues from Twente, from all my former robotics group, and from applied analysis. So we look at discovering periodic behaviors for mechanical systems. So a bit of a different perspective in terms of control, but well, many mechanical system, industrial, bio-inspired robot often need to perform tasks of a periodic nature. For example, could be pick and place, could be locomotion. traditional approach for solving this problem are under the umbrella of periodic output regulation, and normally involves canceling the old planned dynamics and just superimposing a new one with the desired oscillation. But clearly these approaches are not biomimetics at all. They don't exploit the physics, and they definitely not energy efficient. So we wanted to look at the perspective of really learning energy efficient periodic oscillations, and we wanted to have a look at biomimetic, exploit differentiability of the models of physical model, and basically cast the control problem as a neurology problem. So this is a bit the general scheme. So imagine you have, we use this double pendulum, but a conservative open loop system. We have a state feedback control law that is parameterized by this potential mapping here. I will show you more details about it. In such a way that now this closed loop system naturally evolves with the oscillation we would like to have. And we have another loop we call stabilizing controller, because we do not expect to be necessarily immediately on this eigenmode of the system, but we have stabilizing control that brings us there and also keeps us there, because if we add dissipations, clearly the system is going to fall off this oscillation, and we just inject a little bit of energy for keeping it there. So let's see this control by energy shaping. So we assume you have this open loop dynamics, and we have a controller that you can view it as an additional potential energy term to our system, such that the new closed loop system evolves with this energy here. And because we want to be able to be flexible, this V is parameterized, and we use like a neural network for learning this mapping. Although I will show you later on other techniques can be used. So now, okay, we know that we want to achieve a certain closed loop dynamics of this oscillation, but how do we achieve it? So the idea is that we use neural ODs. So we want to minimize the loss function that depends on the task we want to do. In this case, is this L task. We assume like we have pick and place task, where we start from a position, we want to reach a final position and go back. So these loss functions here encode exactly this task. And we want to just solve this neural OD. So we evolve this OD forward in time, we back propagate, we adjust the parameters here such that my system evolves with these dynamics. So these are some results. So it's a magnified version of what you saw before. We start from the blue point. We want the end effector to reach the cross, and we want to go back. So the idea is that we start with the 0 speed, we get here with 0 speed, and we go back on the same trajectory. So that's what like the definition of eigenmode. So this eigenmode loss that you saw before was motivated a bit by the eigenmode theory. We also looked a bit about on that. And you see that this is kind of the potential we learn that allows this system to evolve as we want. Limitation of this is, well, clearly, I mean, it's nice, we can learn it, but this potential is not really interpretable, because, I mean, it's just represented by a neural network. So here's some work I'm currently doing. We try to, similar to the SimURL paper, approximate this neural network a posteriori with a sparse dictionary model to get like an equation. But also, I think I'm also trying to use the L0 model I developed before to directly learn this potential as a sparse dictionary model. The cool thing is that like we show, for now, I've worked, these are really new results I got last week. We can basically replicate the same results of the previous paper, but with this model. And at the end of the day, we get a nice expression for this potential, which has tons of possible applications. Because now, for example, this potential is going to have certain terms in terms of, for example, position of the cues of my system. And in principle, I can even design my system mechanically with some springs such that this behavior is captured. So I think it goes also a bit in the direction of co-design, but I think for us it was really exciting to explore this idea. The second one is that we want to, because before we assume that we have like a conservative system in the closed loop, but we can extend the Hamiltonian formulation to Porte-Hamiltonian formulation to account for dissipation. And there is quite some rich theory about this. So we have our system here that can be the double pendulum, can be any system we want. We want to transform it into a desired Porte-Hamiltonian system where we have this JD, this RD, which are the describe the energy and the dissipation of the system and the energy of the system. These are free terms that with this neural D approach we can learn. So we can actually shape completely the dynamics of the closed loop system, even if we start from a system which has intrinsic dissipation. So imagine we have the double pendulum swinging, whose job with bearings and stuff. At a certain point, it's going to stop. But in this way, if I shape my desired closed loop system such that this RD that includes the dissipation is 0, it means that I'm going to just slightly inject enough energy to compensate for it, and I can keep it swinging very nicely. So seems simple, but there is a bit of a trick here that we cannot achieve any possible closed loop systems. And basically this constraint is given by what is called this matching condition. And this is a PDE we have to solve for all the states. So this is what we are now trying to think about. How can we cast it in probably something like a soft optimization problem as a regularization term? And ultimately, I mean, this one should hold for trajectories that are close to the actual trajectory our controller is going to visit. But that's something we are looking at the moment. And future work, we would like to do some real world experiments because I think ultimately when you work with robots and system in simulation, I'm always very curious to see, okay, what happens if I go to the real world? And we are also looking at extending to electromechanical systems because before, let's say for a mechanical system, we know that this potential energy is only function of Q1 and Q2. But if you have like, because it's a special case, but if you go to a more generic case, like an electromechanical system, your energy function that you learn is now a function of the full state. So you can get way more advanced controller and solutions in the terms. Yes, so to conclude, I show you different perspective on reinforcement learning, what are the limitations mostly. And I want to conclude that indeed current DeepRL techniques are not yet enough for taking like a real world flow control or robot in a flow control problem due to the need for, to the limitation on sample efficient generalization and interpretability. So I think my take from here, I think it's model-based reinforcement learning is definitely good because we can reduce by at least one order of magnitude normally the number of interaction with the real world, although it can be still very prohibited. We can and should exploit prior and symmetries to learn these models of the environment, because indeed, again, this is a way to reduce the need for data because model-based reinforcement learning, as I normally say, your model-based reinforcement learning policy is as good as your models. So if your models are bad, also your policy in nature is going to be bad. We need to do dimensionality reduction in states and maybe actions even, because sometimes you have a very large action space nowadays. We have many works focusing on this multi-agent reinforcement learning to reduce the dimensionality of the action space. But again, without coordination, I see in the long-term potential problems on the fact that each agent acts locally, but then on the global task we want to solve, we're still suboptimal. And I showed you that informing, for example, policies with the parameters of the PD is very interesting and helps a lot improving the results. Would be very great follow-up to see if we can estimate these parameters from snapshots and not relying on the parameter. And I show you different perspective on once we have like a low dimensional space, state space, small enough. I think this sparsity dictionary policy also makes a lot of sense. They can be trained fast and can generalize quite well. Yeah, and that was it. Thanks for your attention.
Thank you so much, Nicolò. Do we have any questions in the audience?
Yes, please. Yeah. Yeah, thanks a lot for question. I just repeated for the Zoom. How does the eigenmode loss looks like? I don't have the equation with me, but I can show you offline. But the idea is that, well, this eigenmode is like periodic motion characterized by the fact that you start from a given, let's say Q0 in terms of position of the pendulum with a zero momentum. You want to reach a point in the middle of trajectory with zero momentum again. And you want to go back to the original point again with zero momentum. So this information, we use precisely this information, like the definition of eigenmode, and we cast it into a loss function, just penalizing well, position and momentum of the system at given time steps. So it really comes straight from the definition of eigenmode. No, it's here is eigenmode. It's just like the type of periodic oscillation we are looking at. Yeah, sorry.
Any other questions in the room? Any question? Oh, sorry. Go on.
Example, and could you elaborate on what the goals were in that example? And then could you also explain what your assumptions were?
Yes. Get this one example here in the wind tunnel. So control, we have like a little motor here. We could control this this flap, so the angle of attack. We have like a 3D printed pressure sensor here. It is covered by this wire, but it's just giving us a bit of information about the flow. And we have, we are inside like a little wind tunnel here that you don't see. We have like fixed velocity as laminar flow as possible. And the goal was, we can measure lift and drag, the drag of this thing through the wind tunnel. And the goal was really try either to maximize the lift, minimize the drag. We tried, or a combination of these things. So they're in terms of reinforcement learning, we get this measurement here as input over time, and we try to predict the action like the angle of the flap. So pretty was simple experiment. Right.
Any other questions in the room? Any questions on Zoom? I don't see anything in the chat at the moment. But if you come off mute, we can try and make sure we can hear you. I'm getting silence. I have one question for you. For the L0 control, when you're doing the KS equation, we're using periodic boundaries for that one.
Yeah, periodic boundary.
Did you notice any so you were comparing like the symbolic form of the different actions that you get? Did you notice anything about the actions like on that that are close on the periodic boundary? Like, are they kind of similar, or does that make sense? So like the top and the bottom.
Yeah. Not necessarily. I think it's I haven't really looked too much into at least if I look at this example, I don't see immediately like a connection. I could dig a bit more into that, but yeah, I haven't seen any kind of regularity appearing.
Gotcha. Yeah. And then on the next slide, when you talk about extrapolation, is there any I guess analysis for why the L1 might extrapolate a little bit better in terms of the cost there?
I think it's mostly on, I mean, here it's a specific instance that I use for evaluating and show some pictures. I think in terms of, let's say, I think for me was more interesting in terms of average reward over different solutions. And I think still the L0 on average would do a little bit better than the L1.
Okay.
But indeed, I don't necessarily have, I think it's mostly related to specific solutions. Of course, there are going to be like some solutions that are a bit better captured by a model, some others a bit less with the other model. So it's really on I would say I showed this example, like specific instances for showing especially that, I mean, using sparse models, sparse dictionary models is a good idea. But on average, I think the performance of the 0 was still a bit better than the L1.
Okay, cool. Do one final call for questions. Oh, yes.
Which slide, sorry?
Wait, space.
Okay, so
Is this part of latent space, the robot?
sorry, I could not hear you, sorry. Oh yeah, the robotics, yeah, the robotics data set, yeah. This one?
Yeah, this one.
Okay.
So
Yeah.
when we do like, control here in the space, we actually have some guarantees that how it's going to affect how it's going to affect.
Yeah, I think, not sure if I understood the question fully, but it's about, well, if I have like an optimal policy in this latent space, how does it transfer to the original space? I think, I mean, guarantees are a bit hard in terms of in the DeepRel world. I would say for us, the guarantee was more on the empirical side. We really saw that these policies, I mean, I haven't shown the rewards plots because you can find them on the paper, or I think less interesting, but yeah, we showed that with this representation, we can do very well, a very good job in reaching targets. We generalized to also different target locations, and we could nicely transfer to the real world as well. So I think we have an empirical evaluation that like a good representation translates into like robust policy that can learn quickly, can generalize, and can be transferred.
Sorry for helping you this time. I tried to find and I found no guarantee, so this will happen. Yeah, thanks.
Yeah, you're welcome.
Any other questions? All right, well, let's